All right. Hello, everyone. My name is Dmitry, and I work at Facebook. And today, I want to share various techniques we use at Facebook to make our builds go faster. The things I want to talk about are either open source, or it's some fairly generic approach that you can apply to your build system or to your code base. I will also try to go into a little bit more details so that you have better understanding how a particular technique works and why it actually helps. And before I go into the topic, just a few words about me. I'm a software engineer in the ads infrastructure team, and you might be already wondering how ads are related to build time optimizations, right? And let me share my personal story here. For several years, I've been working on various features in our ads backend system, on things like performance, stability, scalability, and other buzzwords. And our ads backend is one of the largest C++ projects at Facebook, so it naturally takes a long, long time to build. And when I was working there, I started thinking, I was waiting a lot of time for builds to finish. And our engineers, what they usually do, they start a build and go grab some coffee. Right? I think you all might do the same, but I don't drink coffee. So I started thinking, is it really the fastest our builds can go? Or can we actually make something to make them even faster? Like not so terribly slow. And I started digging deeper into details of the build system, of various techniques we already use at Facebook. And this was all like super exciting and interesting. You probably don't believe me, but anyway. And eventually I started focusing on build times optimizations as a full-time job. And it turned out that it aligns really well with our team's mission. So if ads engineers started to iterate on their code faster, then we can show better ads to our users. And I'm sure everyone likes ads here. And the Facebook revenue will go up, and everyone will be happy, right? So overall, I learned a lot of cool stuff while working there and want to share it here in my talk. Does it work? Nice. OK, so let's start. Here's the things I want to cover today. So measurements, how can we actually measure build times, and why naive approach doesn't work. Then we will talk about actual techniques, how to use open source components to build your build infrastructure so that you can build while you build. And compiler toolchain, how to make your compile faster without being a compiler guy, like me. I'm just a regular person. Code base, refactoring for fun and profit. And the last one will be issues, things that didn't work great or didn't work at all. You'll see when we get there. OK, so before we actually start, let's talk about why we care about build times. So how many of you have long builds? All right. And how many of you check emails when they wait for the builds? Or maybe Facebook, Twitter, anyone Google+? No? And after you checked, how often you find yourself on Wikipedia after 2 hours reading about quantum mechanics? All right, yeah, I've been there too. Maybe you like fighting on swords? Yeah, we all do. And OK, I don't have exact numbers, but we have roughly speaking 20,000 people working at Facebook, and many of them do write C++. No, it's not like all PHP. We have some C++. And we just don't have that many swords in our office, right? So we have to make our builds go faster. And before we can improve things, we need to learn how to measure them. There was one famous guy in the end of 19th century who said that, and I think it's still true today, even after 100 years. Without proper measurement, you are really blindly going anywhere and just not really knowing any direction. And it's really, really hard to find bottlenecks when you don't have any measurements where you can do things. And I actually have one war story I want to share before we jump into this topic. So when we started measuring and analyzing data, we found exponential algorithm in our Thrift compiler. How many of you know what is Thrift? How many of you know what is Google protobuf? Okay, a little bit more hands. So it's pretty much the same thing. And you can think about Thrift as a domain-specific language that helps you describe your interface of your service and then generate some code based on that. So here is an example of Thrift file. So we have some file a.thrift, and it has some description there. So the nice property of Thrift, it has includes, right? So you don't need to put everything in one giant file. You can have nicely organized structure. And so you can include the file and then use the types from there. Then you can run Thrift compiler that will generate some files like types, reflection, and other cool stuff. So when we started measuring build times, we found that some of our files take several minutes to compile. Like not C++ compile, but Thrift compiler. And what Thrift does, it reads some bunch of text files and writes some text files. It does not do any like fancy optimizations there. It's like all relatively simple, but several minutes. That was really crazy. And we started digging deeper into what's going on. So let's look into some example. So we have file A that includes file B1 and B2, and we have file C1 and C2 that depends on these files. So when we need to parse file A, we need to know all the types from dependent files. So in order to do that, Thrift compiler goes recursively. It runs itself on B1, and it needs to parse it. So it needs to know all the types in B1. And to do that, it needs to go recursively to C1 and C2. So when it does that, we go and process file B2. That will go and process file C1 and C2. So I guess you see some pattern here that we found this bug, or maybe let's call it a feature, that Thrift compiler does not save any intermediate information, so it will recursively jam into the source tree and will process the files over and over again. So if we have like n layers here, like up to z, then the bottom layers will be parsed to the power of n times. And it was really, really slow. The fix was quite simple, just add some caching there, but the amazing thing that the bug there was like feature. It was there like for ages, like since the Thrift was first built, and it was like 10 years ago. Okay, so how to measure build times? One approach we can do is to just instrument developers' machine, right? They do a build anyway. So let's add some logging, write to database, and then analyze results. The thing is, there are multiple factors that prevents you from getting like non-noisy data. The data will be really noisy. So the engineers, they can run on their builds on different hardware. Like someone may run builds on iPhones. I hope not, but someone might do. And the workflow can be different, right? So like someone might modify just a few files, like on the small project, other will be building an entire universe. And they can experiment with different build options, right? So some engineers just try all the possible optimizations. Others are fine with just compiling their code, and they're done. And also, there could be something else running on the machine, like multiple builds in parallel, or Bitcoin mining, whatever. Like people just do some weird things sometimes. And there are also the problem with sparse points. Like engineers don't normally work on the weekends, so sometimes do, but we will get like not so many data points there, and the data will be like super noisy. So what we did? we decided to build some separate jobs and deploy them to separate servers, right? So it's like continuously running. So it's like checks the latest revision, builds it, modifies some files, builds again, logs to some database, and over again, like very tirelessly trying to get some good data points. And it's all good, right? We have like hardware configuration. We know, and it's all like fixed, so it doesn't change from time, and we can control environment there and not run some weird processes. Like we would better do this thing. We also thought about some workflows for engineers. So we decided to select some workflows that I think we represent what engineers typically do when they work with their code. And let's look at the workflows. So we decided like there are three like different workflows. One is clean build. You check out your new revision or rebase to latest version. You don't have any changes there, so you just build it from scratch, right? And what essentially this workflow means that you don't have any local changes, so we should be able to take it from the cache. And we will talk later about the cache itself. Another workflow is some large changes. So you build it once, and then you try to modify some headers, like in some core library. Bless you. And then it just triggers a massive rebuild of your project. So when it usually happens, like I think everyone might have their util.h file there. Just people put their favorite functions, and when you go and add your favorite function there, you just rebuild the whole project. We have like multiple files like that. And it could be the small change. You modify a CPP file, and it needs only build this one and just link the result. And in this workflow, what really dominates is the link time. So in a nutshell, these three workflows, they kind of represent three different aspects of the build infrastructure that we care about. First one tests the caching layer. Another one tests how build system handles many files. And the last one is linking. Okay. And let's talk about the infrastructure. So I have a question for you. What do you think is the most important part of the infrastructure? Any guesses? Compiler? Yeah, that's a good one, but kind of that's the part that's hard to remove. Okay. Disk.io? Is it correct? Is it what you said? No, that's I meant the different one. You? The suggestion was number of cores. Okay, I'll tell you what I actually had in mind as the most important part. It's build system, right? So how do you build stuff without having a build system? And internally we use Bach to build C++. It's open source, available on GitHub. It even has some documentation if anyone wants to try. It's also a general purpose build tool. It can be used for Java, C++, Haskell, like your favorite language. And we just recently open sourced C++ specific wrappers that should help building other open source projects with Bach. And what are the key features of the Bach we use? First one is reproducible builds. So it means that the Bach runs build in the sandbox, which isolates the build from your environment, and it should behave the same way on any other computer. The second one is incremental builds. Bach does not use timestamps to track the files. It uses the actual content, so it can know that something needs to be rebuilt and does not try to do unnecessary job. And also, Bach was designed with built-in cache mechanism. This was done from the very beginning, and it has native support for that. And now a really brief overview how build rules look like. This will be useful later when we will talk about actual optimizations. So we use this declarative language where you specify your sources and dependencies between them. And then the bug can go and execute this in the right order. So in this example, it will, if you have questions, let's do them in the end of the talk. So in this example, it will run all CPP, it will compile all CPP files in parallel and then do the linking in the right order. This is kind of simplified example. In reality, there could be more steps, even not C++ specific, something like running Thrift compiler or custom shell script. So in reality, it might look like this. Does anyone heard about Folly? Yeah, so this is the graph of Folly. And it's like fairly tiny project. Like we have way bigger projects that depend on Folly, and the graph already is quite complicated. But the bug can handle such graphs perfectly fine. Okay, so let's talk about how bug achieves incremental builds. The key concept here is rule keys. The idea is to encode some information into the rule key so that if the rule key does not change, then we don't need to make a rebuild. So in this example, we will hash some global variables, global parameters like bug version, toolchain versions, compiler flag, some environment variables, then add some build rule specific stuff like sources and dependencies and put them all together in the cache key. And there are different types of cache keys, and they differ by what we do with dependencies. So we will talk about a little bit later, but now let's see how it actually works. So we have a rule key. We go to the bug cache, try to fetch the output, and if we are lucky, we will get a cache hit. And we will get the output. And if we are not lucky, we would need to rebuild the rule, and then we will store it to the cache. Looks simple. And so for different types of rule keys, so there are 3 main types, and there are others, but they are not C++ specific, so I won't cover them. So there are default keys, input-based, and manifest-based. So I have another quick question for you guys. Does anyone use a Ccache? Does anyone heard of Ccache? Okay, a little bit more hands. So basically, the third type of rule keys in bug, the manifest-based, they work really similar to what Ccache does. So let's start with that. So let's suppose we have file a.a, and which depends on headers a and b. So we want to get the output file. So how we do that? We hash the file and then try to, oops. Okay. Oop. It seems like something is missing, but we hash the file and get the manifest, like this, this gray rectangle there, and it contains several things. So the purple one is a hash of file A and the path to it. And the blue one is the same for file B. So we get a list of files that A was depending on, and we can check the actual state on the disk. And if it matches, we get the cache hit. So we take another hash, which is green here. Sorry for inconvenience, and we can fetch it from the cache. So that's how Ccache works. However, this mechanism is really C++ specific, and it's also fairly slow. We need to do 2 round trips to the cache, and we also need to compute the hashes of the several files on the disk, and this can be quite slow. So bug has 2 other mechanisms, 2 other rule keys. This is default rule key and input-based. So the default rule key is the one that's computed recursively. So to take the rule key for target 1, we need to first calculate the default rule key for target 2. And we do this based on the default rule key for target 3. So it's kind of recursive thing, but in reality, it's actually really fast. We just need one traversal for the graph, and we combine all the information back. On the other hand, the input keys, they use the output of some rule. So if for rule 2 the output hasn't changed, then we don't need to rebuild the new file. Okay, so let's talk about bug cache. So the bug cache, it has the two types of bug cache. So one is dir cache. It's the file on it uses the directory on your local machine to fetch and store artifacts. And it's useful in things like you check out a new branch and then go back, or modify some file and revert the changes. But sometimes it does not help. Like if you check out the fresh revision, there is nothing on your machine that will help you, right? So the bug has this concept of HTTP cache. It's something in the cloud. So that's a cloud for that. And we use continuous integration to populate this cache. So there is the continuous integration, it builds the artifacts and uploads them to the cache. And then the clients can check it, and it actually works quite good. However, there are some problems with that. So here is the model of our repo. We use monolithic repo with many projects there, and the green dots are the commits for which the cache was populated. And you are the user, you get the fresh revision, check out the latest one, and tries to build it. Seems good, but it turns out that the second commit here is some change to Folly. It's our core library that everything depends on. So basically, this commit will invalidate the whole cache. And the cache becomes useless here. And you wait several hours and become not happy. So what we decided to do is to build this rebase to can build script. The idea is continuous integration when it runs on the project. It will write to database which commit it populated. So when the user wants some specific revision, it will query the database, get results, and then check out this revision. However, there are some problems here. First of all, we need to educate all users to start using this script, because they need to provide the input, like which project they want. And we have many developers, and it's really, really hard to educate all of them. Another thing is, what if you want to work on multiple projects, like project 4 and project 2? And which commit you will choose? It will be suboptimal, like either way. So we built another mechanism. We call it warm revision. And the idea is that once enough con builds were populated for specific commit, we will mark this revision as warm. And then the source control client will use that by default. So we have our own wrappers on top of source control client, so we can actually inject any functionality we want there. And it works quite good. So, and what happens if you build multiple different projects? So suppose in this example you build project 1 and project 2. So it turns out that a lot of projects, they share core libraries. So you will, even if you don't get a full cache hit, you might still get a really good one. Okay, so as a quick comparison, we have two mechanisms, rebase to con build and warm revision. Rebase to can build provides about 100% cache hit rate, and it's really, really helpful. It helps us to reduce the build times from like hours to just several minutes. But it requires education and suboptimal with multiple projects. On the other hand, warm revision is about just 30% slower in our cases, and it works by default, and everything is great. Okay, so now you can check out your clean build workflow, and it works great. So what happens if you have many files that you modify, and caching workflow cannot really help you here. So we use DCC. How many of you know what is DCC? Okay, that's good. Yeah, that's a pretty ancient technology. It's been there for decades, but it works surprisingly good. The way it works, we compile the file, we preprocess file locally, send it to remote cluster, and then get results back. So this really helps to move CPU-intensive work out of your local machine and not be bottleneck on number of cores or CPU there. Okay, so often the disk becomes the bottleneck for the builds. And there are some simple ways to help here. One is to take SSD disk. Sounds simple, right? But it could be quite expensive and not available to put there. So there is poor man's approach, like put your builds on TempFS. The trade-off is you will have less memory for other things, but it might be a good trade-off. All right, so let's talk about compiler. So we talk about infrastructure. Now let's go a little bit deeper. And let's talk about build modes. So the build modes is the thing we use to distinguish different purposes. So we use mainly two build modes, dev and opt. And one is for development, and another is for deploying to production. So naturally, they optimized for fast compilation versus fast runtime. So the developers, they usually use their dev mode when they test locally, but when we deploy to production, we need to be really fast and efficient. And so we use different compilers there. One is Clang for dev mode because it's just faster compiles, and GCC usually produces more optimized binaries. And so we disable all optimizations in dev mode because, yeah, let's make it compile faster, no matter how slow it will run. And we use dynamic mode, dynamic linking as a linking step. Let's talk a little bit about linking mode. So in dynamic mode, and the difference between them. So the dynamic linking is quite cheap. So you kind of need to only reference your dependencies. And you also can do incremental linking. So you can start linking like libraries as they build. While for static modes, they package everything into one executable. So you need to wait for all the jobs to finish, to start linking step. And also the files might become really huge. So essentially, if you build like hundreds of tests, then each of them will contain the copy of some library. So, but static linking is more friendly for deployment. So you just take this file, deploy to production, and not worry about dependencies. Okay, so let's talk about how to speed up compiler. So one thing we found, it's just let's update it. And in the April this year, we got about 20% win just by updating our compiler. There are more details in the LLVM mailing list. And really thank you everyone who is working on LLVM. We are super happy to get these free wins. Okay, so what else can you do with compiler? Okay, there is this thing called profile guided optimization. How many of you heard this term before? Nice, okay. So, and we got about 10% win in our compilation times by using profile data when we build our Clang compiler. So we used profile data from Folly, as we think it represents the workflow, the code base quite well. And it kind of complicates your update compiler step, but if you automate this, then you will preserve these wins for future updates. Okay, so let's now talk about how we can speed up linking. So let me show first what's the problem here. So suppose you have large build tree and you modified some CPP file in the leaf nodes of the tree. Then you will get this linking chain that goes all the way to the top, and it can take quite some time. So how we can make it better? So one thing is to just link less data. So if you use this flag visibility in lines hidden, it will take inlined class member function and not put them into result in shared object. And we got really huge wins, like 50% in the link step, just because there is less data there. Like it just compiles faster, it links faster. However, there is one problem with that. Does anyone know which one? No? Okay, so the problem is static variables. In this example, there is variable val that kind of shows how many times function bar was called. And if we use the flag mentioned on the previous slide, each of the files, test1 and test2, will use their own static storage. And this kind of becomes a bug, right? So you expect your output to return 1, 2, 3, but it returns the different things. Fortunately, there is a solution for that, and actually 2 solutions. So one, you can move your implementation to source file. So once the function is not inlined, it works fine. And the other one is to annotate the function with this attribute. So if for some reason you still want to preserve inlineness. Okay, so that's good. What else can we do with dynamic linking? First of all, let's explain another problem. So suppose you do some implementation only change. So in this function answer, you return 42 instead of 0. And then it again will create this relink chain in your build process. But in practice, you would just like be fine with changing the result library with the new one, but the build system doesn't know that. Okay, so really quick overview of ELF. So ELF stands for executable and linkable format, and it's really quite complicated. So kind of what you need to know about it, that it has metadata and a bunch of sections. And turns out that the linker actually needs only three sections from this file: dynamic, dinster, and dinsim. So if we can somehow remove other sections from the file, then from the point of view of linker, the output won't change, and the build system will know that it doesn't need to rebuild the whole binary. So we put some post-processing on the ELF files. So we first compile, get shared object file, then run post-process by removing all sections rather than these 3 ones. So it looks like this. So the file changed, library also changed, but the library interface did not change. And let's see how it helps with the relinking. So we have this scheme, and if we replace all libraries with this interface, then from the point of view of the linker and the build system, it only needs to relink the library 7 here and doesn't need to relink the whole tree. Okay, so how to use it? So you can, if you use bug, probably a lot of you guys use, you can put this option in config. Very simple. Or if you don't use bug, you can implement this in your own build system by just using opt copy. The thing to note here is that you need to change section address as well, because if you remove some sections, the other ones might get the different address, and it will introduce the noise in your linking step. Okay. Also, we've been talking about dynamic linking, but there are things we can do with static linking. There is this flag which you can pass, and it will run linking in parallel. In practice, we found that n equals 4 works perfectly fine, and it's kind of the best points on trade-off curve, and we got about 30% on the link step in this case. Okay, code base. So what can we do with code base? Okay, this one is fairly straightforward, but still worth mentioning. So if you have large file, you often will wait on this to finish. So what you can do is you can split into halves or in more parts and reduce the bottleneck time. Yeah, very straightforward, but still very effective. Okay, template instantiation. So there is this interesting feature like extern template, which you can use to save on template instantiation time. The thing here is, once you do that, instead of instantiation the template in every translation unit that includes foo, it will be instantiated only in CPP file, and you will save some time. Though you need to use this like carefully, because it might be a manual process to do, and if it does not give you wins, then what's the point? There is another problem here, that if you include foo, then you also need to link with foo CPP. And in some build system, it might be problematic to enforce correctly, because their messages, they're just not great. But in Bug, we're able to track the headers, so we know that you cannot really use some header without depending on the specific target. Okay. Yeah, that's probably sounds surprising to you guys, but apparently there are some cases where using templates can actually help you with your build times. And we got about 50% wins for certain files. I will not go into details. There is Eddie who will give a talk tomorrow on that, and feel free to go to the talk if you're interested. All right. Okay, so you have another problem. So you have your nice library foo, and you perfectly crafted all dependencies there, and it works great, but suddenly, boom, someone added some like giant dependency somewhere deep inside your dependency tree. So how actually you solve this? It could be like really large, and we've seen on the Foley example that the build graph sometimes not manageable to do. Fortunately, we have mechanism for that. We have query language built into the Bug, and by running this simple command, it will show you dependency graph between these two targets. And then you can run and visualize it. So it might look something like this. I'm not sure if it can be seen, but there is on the bottom your target, and you can now reason about the graph and see which dependency, where this dependency was added. All right, issues. Okay, so yeah, we tried some things and they didn't work that great. And okay, let's talk about them. So one thing we did long time ago, I think even before we were using Bug, we were populating the cache from developers' machines. So what happens? It felt natural, right? So you build and then you populate instead of just set up in some continuous integration, whatever. And turned out that this is sometimes doesn't work. So it works, but it actually uses a lot of space in your cache for no reason. So if you have some build options, experimenting with build options, it will create a separate universe in the cache. Or if you have your local changes, it will also upload them to the cache, but probably your colleagues does not make that similar changes so they can benefit from that. And also we had data corruption, like when someone was working on build system and changed the way cache keys were calculated, it uploaded the incompatible artifacts, and when these artifacts were fetched for other developers, they get some really strange error messages. So writing to cache from developer builds, how about no? Okay, and next thing we tried was Clang modules. Yeah, everyone excited about modules and how they help with build times. So worth noting that this Clang modules is not the same as modules TS. The modules TS is fairly new thing and it's being developed, while Clang modules, it's been there, I think, since 2015. And the last year on CppCon, Google folks made a talk how they use these modules in production. And we are super excited to try it and adopt for our code base. Let me give a brief summary how they work. So basically, you don't need to change any syntax of your code. You just put these module map files along with your sources, and they explain the module interface. And then the compiler will know how to deal with this stuff if you pass some special flags. The nice thing that it doesn't require any changes to your code base. I mean, code base itself. Like you don't need to put some weird imports in your code that not all compilers understand. And you can do incrementally transitioning for more and more files. Okay, looks great, but apparently we started experimenting with this and found a number of small issues which we managed to work around, but we also found a couple of major issues. So this one we reported in April this year, and basically the Clang will crash when using capturing lambdas like this. So we have quite a few places in our code base where we use lambdas. So it was not great for have compiler crashing. And the second one was this one. So we reported it in July. And there was not crash this time. Fortunately, that was good, but it was quite weird. And basically it meant that some name had same mangled name, there's another definition, but it was for the same function. After some experimenting, we found that this happens when you pass lambda from templated function. So in this example, if we remove templates from function bar or pass something else, not lambda, to class f, then it works fine, but with these conditions, it's not. So, and again, we have quite a few places in our code base, so this slowed our adoption. Okay, so I think that's mostly it. I guess I was too fast in some places, but okay, so let me summarize the things I talked here. So I think one of the most important things is to actually think how you measure your builds. Like you can probably not start measuring, but started thinking like about your workflows and how you what the bottlenecks could be is really helpful. Caching and distributed builds were the most effective things to speed up the builds, and it's fairly easy to use them. Like Ccache and GCC, for example, they provide some transparent wrappers that you use instead of your compiler, and it works under the hood. Also, you can tune your compiler without going into internals, like just update it with new version, and people working there to make it faster. And you can always refactor your code base to make it more compiler friendly or use some techniques to save here. All right. Yep. That's it. Okay. Please use mic. Yep.
I'm kind of curious if you guys use what is it, Unity builds?
Oh, yeah.
Or that sort of thing. Do you guys use those?
No, we don't. So so the question was, do we use Unity builds? And I assume by Unity builds you mean like putting a lot of CPP files into one like giant CPP file and compiling those. Yeah. So we don't use this. We actually sometimes go the opposite approach of trying to split them, because often you have your large file and you can increase parallelism by splitting into multiple pieces.
Excellent. Do you do that because your link times don't end up being sped up by this, or?
So it's not only link time. So if you put everything into one CPP file, the compilation time for this can increase dramatically.
Mm-hmm. Yeah.
Yeah.
But
I guess like we didn't really
would your link times not get better? Like if you took 100 things and you turned them into 10 things and then you linked them together, you'd have 1/10 the data to link though. And I thought.
I see. Yeah. So The question was maybe the link time then getting improved. So in our experience, the link time, they are substantial, like a couple minutes, but the majority time you spend compiling the files. And if you use dynamic linking, then the linking becomes even less of a problem.
Okay, thank you.
Okay, thank you.
Do you use Gold BFD or some other linker?
I think we use Gold. Yeah, that's what I know. Yeah, the question was, do we use Gold, BFD, or any other linker?
I was trying to understand what does the cache actually contain? Is it like an O files and the hash of the CPP and H files?
So the question was what the cache actually contains. And do I understand correctly, you mean like general cache or like this manifest-based caching? Okay.
I'm not sure which one, but the one for C++, which...
Yeah, so actually cache contain like multiple, like can contain different things. So for default keys and input-based, they contain the actual artifacts like .o files. And for manifest-based keys, they contain two types of artifacts. One is manifest that describes your like caching state to some extent, and the actual object file. So actually, bug cache is kind of general purpose key value storage. So in some cases, we store some additional metadata, not only the object files.
And if you want to protect your code base from other users of that cache, is it safe? I mean, if you don't want to expose the code itself.
Yeah, I'm not sure if I understood.
If I have access to the cache, do I have
okay, can you
even if I not supposed to see the code base it was based on?
I see. So I guess the question was about security. If we have things in the cache, kind of, do we protect it from other users? Is it?
Yeah, even if I'm allowed to use the O files, but not allowed to see the code base.
Yeah. I guess we don't have such cases as you're not allowed to see code base. So kind of, we have one monorepo where like people just check it out and use it. So there is no such problem that you are now not allowed to see like particular code. It's like basically open for all developers.
Okay.
Thank you.
I have a lot of questions, but I'll ask.
We can also follow up offline if you're interested, but you can ask some.
Yeah, we'll talk offline. I have just one question for now. You mentioned the HTTP cache, and you mentioned a local cache for the developer on his disk. Is it a true second-level cache in that if he's doing a clean build and when he gets the stuff from the HTTP cache, he adds it to his own cache?
Yes. The question was, is it two-level cache, a dir cache and HTTP? And the answer is yes. We always try to populate the local cache, even if we fetch information from HTTP cache, so that it can be useful later if you switch branches or go to previous state.
Hi, thanks for your talk. I had a couple different questions. The first was, well, LLVM supports a few different methods for collecting profile information. There's the front-end based, late IR instrumentation, and sample-based PGO. Which ones have you tried, and which ones work best for you?
The question was what type of... if I understand correctly, the question was about different types of collecting profile data. Actually, I don't know, but we have Igor who might know more. So I guess the answer was we built Clang with GCC, like with other compiler, because GCC produce faster results usually. So we use the mechanism built inside GCC.
Okay.
But you can come and talk offline. I guess that's the expert here.
Okay. The second question was kind of unrelated to build times, but about your debug configuration. So you're using Clang with modules and shared libraries?
So we don't use modules because we hit number of issues.
Okay.
And what was the other thing?
Oh, the third one was going to be about how and if you use PGA with the Swift compiler, if at all you do. I can ask.
Okay, maybe let's talk offline.
Thank you.
So yeah, you showed the example about this new dependency that was changing the build.
Yep.
What kind of metrics did you use to figure out what dependencies might be problematic?
Yeah, so the question was about this finding unexpected dependencies and which metrics we use. Let me think. So I don't think we actually have any metric. We kind of just use the general sense. So if we see something is big, then it might be worth optimizing. But unfortunately, it's kind of hard to analyze the graph itself with the metric.
With your release builds, what size are your ELF files, like, say, with the debugging information for your release ones? I guess those are fairly large things. Like, around what kind of size do you guys end up working at? Because you're saying like a couple-minute build times.
Yes.
So I'm kind of wondering what that.
So the question was about size of our resulting like binaries in release mode. I think it's a couple gigabytes.
Just for one executable?
Yeah. Is it large? I don't know. It's like so. And if you have
a couple of gigabytes, okay. No, I think that's in the right scale. Okay, I'm seeing about the size.
So if you have kind of many tests, as I explained, then each of them will be a couple gigabytes because they essentially contain all the like libraries.
Okay, cool. Thanks.
Do you have any tools as part of like your continuing integration process that help you route stuff like missing for declarations that could reduce includes in header files and like trim the dependencies to a minimum to improve incremental builds?
I see. The question was about tools for forward declarations. So I don't think we have any tools. We tried using like include what you use in the past, like long time ago, and it didn't work. And I don't think anyone remembers why, but so we don't use it right now.
Okay, thank you.
Apologies if I missed this. Did you say what your build times were when you started and what you managed to reduce them to?
Yeah. So the question was, what was the order of changes when we started? And so kind of the changes I described were on the like time span of like multiple years. So it's not like we kind of started and then finished. It's like ongoing process, but kind of the order of magnitude, if we turn off the like caching and other optimizations, it might take several hours to build. If you get a perfect cache hit, you just get a couple minutes, like maybe 5, 10. Okay.
Did you try precompiled headers?
Yeah, great question. So that's kind of the things like include what you use and precompiled headers, the things I was planning to include in the talk when I was preparing, but turns out there are not so many interesting details there, rather than we tried, it didn't work, and kind of people don't really remember why, so probably it's a good point to go and revisit some of the approaches.
I don't know much about Buck, but will Buck help you with precompiled headers?
Yeah, we actually have some, when we were trying to use precompiled headers, we added support to Buck, and I think we even added the like multiple precompiled headers, like so you can use different precompiled headers for different libraries. But I guess there were some issues there. I honestly don't know details.
Last question. You used distcc. Did you have to change your code base at all or your build system at all to maximize the efficiency of distcc, or was it sort of just turnkey? You just got it. It just worked.
I don't know if we do anything. So the question was, how did we do anything to improve efficiency of distcc? As far as I know, no. We kind of turned it, but maybe something was done kind of before I started the research in the things.
Oh, thanks so much.
Yeah, thank you.
So you mentioned you use distcc. I'm curious, How fast of a network do you have to make that reasonable? Because when we use it, we always run into the network bottleneck.
The question was, how fast is our network? I don't know, but it's very fast, so it's not really a bottleneck there. So we kind of have all infrastructure like inside data centers, so we don't need to it's fairly fast. Yeah. Sorry, don't know, just don't know the actual numbers, but.
Thank you.
Okay.
One more question. Have you heard about or tried ZapCC?
ZapCC. No, I haven't heard. I guess it's an analog of DCC.
It's not quite analogous. It's supposed to be a server client-based compiler that it stores state. So you can keep asking to compile more and more files, and the first one takes the longest, but the subsequent ones it does much faster, and you can do incremental builds.
Interesting.
So
do you guys use it?
No, I think it's only just barely out. It's not. It's. I haven't tried it yet.
Interesting. Okay. Yeah. I hear about first time about it, but thanks for pointer. Okay. Interesting. Okay. Okay. I guess that's it. Thank you.